Conditioning is a very useful tool. When we do not know how to proceed unconditionally, we can use the conditioning and tackle the whole problem piece by piece. Additionally, it provides some extra insights in many arguments. This video discusses 4 exercises to show that conditioning is very useful in solving problems. And if we understand the conditioning well, it can help us to understand many pitfalls and paradoxes we see in our daily life. Now let's proceed with the first exercise, and where we're gonna use the conditioning as a key to solve this problem. So consider we are playing a game starting with $1. We flip a 3-sided fire die. If we throw a 1, then we lose $1. The game ends. Okay. If we get a 2, we keep the dollar, and we can keep going with the same game. If we throw a 3, then we win $1. The question is, what is the probability this is a never-ending game? So the game ends when we have nothing left in our hand. And it could be the case that you throw 1, you lose $1, the game ends. It could be also the case that you keep the dollar or you win the dollar and the game keep going, right? So what is the probability that this is a never-ending game? We can pause the video at this moment and see if you can solve this problem by yourself. Okay, now if you want to calculate the probability of this is a never-ending game directly, it's going to be very hard. But instead, we could consider the complement of this is a never-ending game ANJ, right? The complement of this ANJ is the event that we lose all the money, starting with $1, then the game ends, right? So the game ends in the end. And what is the probability of that? If we define D as the complement of ANJ, essentially we need to calculate PD, the unconditional probability of event D. You can pause the video at this moment and see if you can solve the remaining. Well, at the start of the game, we have $1, right? And there are 3 options to go. We lose the dollar, we keep the dollar, we win the dollar. This is the additional hints on how to proceed. You can pause the video at this moment and try to figure out all the remainings by yourself. Otherwise, we keep going. Okay? So it's not very easy to calculate the unconditional probability of event D directly, but if we use conditioning, we could tackle that piece by piece, right? This is law of total probability. It's not easy to calculate this one directly. Then let's see if it's easier to calculate conditional probability instead. Okay, the left-hand side equal to the right-hand side because we have a partition over there. We either lose $1 or keep the dollar or win the dollar. So this is a partition of the whole sample space. And we know each of these values are all equal to 1/3, right? Because we are throwing a 3-sided fire die. The remaining challenges are here, how to calculate those conditional probability. The first one, if we lose the dollar, well, for sure, the game already ends, right? We lose everything in our hands. So it's equal to 1. If we keep the dollar, then we can start the exact same game again. So this value is actually equal to PD. PD is unknown for now, but let's keep it there, right? Because it's very closely linked to the value we want to deliver in the end, so we keep it. Then how about the third one? The third one is really challenging. Now you win the dollar. So you're gonna start the game with $2 in our hand. Well, think about this. You could proceed as if you only have $1, and in the end we'll lose everything. You look back, oh, there is an additional dollar here. Then you could repeat the exact same game again. The dollar won here is more like serves. It could be serving as a second life, right? That's exactly what happens to Wade in the movie Ready Player One. So we have to lose the game twice in order to lose everything if we consider all the game started with $1, right? And the dollar win here is more like a second life. So this conditional probability, well, given we need to lose twice, is the probability of d to the power 2. Now, if we summarize everything altogether, this is what we have, right? So PD is equal to 1/3 plus 1/3 times PD and 1/3 times PD to the power 2. If we solve this equation, we'll find out PD need to equal to 1. This is very easy to say because this equation implies if we multiply by 3 on both sides, 3 PD equals 1 plus PD to the power 2. And now we move this one to the other side. What we have is PD to the power 2 minus 2PD plus 1 equal to 0. And notice here is essentially PD minus 1 to the power 2 equal to 0. So the only value could be taken by PD is 1. Now if we know PD is equal to 1, because NEJ is the complement of D, we know the probability of a never-ending game is equal to 1 minus PD, which will be 0. So the game always ends in the end. This exercise shows that, well, even though calculating the unconditional probability directly is very hard, once we use conditioning, everything can be solved quite easy, right? Sometimes it's easier to work with conditional probability. So next, let's take a look at another exercise. We know econometrics in the Netherlands is a very welcome and, well, I would say challenging major to study. And we want to know the effect of studying econometrics on wages. So suppose here, so we're gonna have 3 different events here. Doing masters in econometrics, let's denote that as event E. And we also have earning high salaries, right, and low salaries. Different events here. Research shows that probability of H is 6/100, and the probability of H given E, well, indeed this posterior updates the prior by a very large number, okay? Actually 10 times. So should we study econometrics to get higher wage? Is it always true? Well, there could be some additional event lurking in the background. Suppose it would be event whether or not you like mathematics, right? M. Why this event might change our understanding of this problem? Let's take a look at this simple example. Suppose we have a sample of 100 students. Those are the students learning econometrics in color blue, and in color black, those are the students who like mathematics quite a lot. And those yellow dots denote the one in the end earn high salaries. Then we could calculate a lot of different probabilities. So the probability of earning high salaries gonna be 8 out of 100. And the conditional probability of event H earning high salary conditional on doing econometrics can be 3 out of 5, right? There is a 3 yellow dots out of 5 blue dots. And the pH given like in mathematics is 6/8. So there are 6 yellow dots over, right, over those 8 black circles. We can also calculate some additional probabilities here, conditional on the joint event of liking mathematics and doing econometrics. The probability of earning high salaries given this joint event M and E is 3/4. And the conditional probability of earning high salaries given not liking mathematics is 2/92. Because there are 92 not liking mathematics, and among this, there are 2 yellow dots, right? And there is a set 0. So conditional on the joint event of not liking mathematics and doing econometrics, the conditional probability of earning high salaries given that joint event is very set 0 there. From these numbers, what we can learn is H is indeed not independent of E. So by conditional on E, by doing econometrics, indeed the conditional probability of H given E is much higher than the unconditional one. But what more important is, well, H is independent of E given M. So once we know whether one likes mathematics or not, it doesn't matter anymore whether this one does econometrics or not. Right? Look at here. Knowing this one also studies econometrics does not update the conditional probability given we already know this one likes mathematics. The number remains the same. So what actually drives the high salaries is whether or not liking mathematics, right? And H is conditional independence. Once we know what event M, it no longer matters whether E or not. And H is not independent of E given not liking mathematics, right? So conditional on not liking mathematics, the conditional probability of earning high salaries given not liking mathematics is non-zero. But if we now learn something extra, like these ones also doing econometrics, but they are not liking mathematics, the conditional probability here is updated to a lower number, 0. So what we can learn here is seem to be that what fits is best, right? If liking mathematics, it doesn't matter whether you do econometrics or not. If not making mathematics, it might be better not doing econometrics. Wow, is this the correct answer then? So basically what we can learn here, there's some underlying events driving everything instead of whether study econometrics or not. Is this the correct answer then? Well, the fact is quite negative that we don't know. We do not know because there could be other omitted events in the background, right? To understand the underlying rationale or underlying causality, we'll need more data, more designs in order to do a thorough data analysis. And it's not always easy to do a decent research. What we can learn from this simple exercise is simply that, well, conditional probabilities doesn't necessarily mean everything. There could be some missing events, and sometimes the conditional probabilities, they are not everything. They are definitely not equal to causality. If we really want to know the underlying channels, what is the underlying models, we'll need to do a lot of more work. And the second lesson we could learn from this exercise is if there are some omitted underlying events, right, they could change our understanding. Like if we ignore the event M, then we're probably gonna draw different conclusions. Okay, now let's take a look at the second exercise, which is a prosecutor's fallacy. So here is a tragedy. Sarah Clark was tried for murder after 2 of her sons died shortly after birth. During a trial, an expert witness for the prosecution testified that the probability of a newborn dying of SIDS was 1 over 8,500. So the probability of 2 deaths, he kept going, due to cysts in one family was 1 over 8,500 to the power 2, or about 1 in 73 million. Therefore, he continued, the probability of Clark's innocence was 1 in 73 million. Well, the whole argument seemed to be plausible, but what do you think of this line of reasoning? I hope you can pause the video at this moment and think what are potentially mistakes this expert made. Okay, if we translate the story into mathematical formulas, it's basically say, well, let's denote D1 as the first death due to cysts, and I denote the event that Clark is innocent. And we use D2 to denote the second death due to cysts. Okay, what he claims, what the expert claims, is essentially that the PD1 conditional innocent is 1 over 8,500, and the probability of this joint event conditional Clark is innocent is 1 over 8,500 to the power 2. Here is already some potential mistakes, right? Because D1 and D2, they are not necessarily, well, conditional independence given I. It could be the case there could be some genetic flaws, right? So if we observe the first death due to cysts, then observe the second death due to cysts, the probability might be much higher than this value. Okay, but even if we ignore that, here's another more serious issue. Then the expert states that therefore the probability of Sally Clark, right? Sally Clark's innocence was around 1 in 73 million. So basically he means this conditional probability of I conditional on this joint event, D1 and D2, is essentially equal to this conditional probability. But we have already learned that PA given B in general not equal to PB given A, right? Actually, according to the Bayes rule, this is what this value is supposed to be. And under the presumption of innocence, that means if we choose a very small value for the probability of being guilty, so the whole term here is quite small, because this is a value, right, within 0 and 1. If suppose we choose, for example, 0 to this value, look at the whole monster here. This is essentially 1, right? So what the expert says is not correct according to the conditioning idea. It seems to be counterintuitive, but actually not, because consider the large population we have, then whatever extreme small events, it could happen to someone, and that does not make those people guilty, right? So this is a paradox. And what about a new paradox here? The third one is a famous paradox called Simpson's paradox. Right? Suppose we have a job consists of 2 tasks. You know that at both tasks, you are outperforming your colleague Jim, who is sleeping half of the time. At one point, your boss calls you in and says, Bert, you are not doing well. Even Jim, who's sleeping half of the time, scores better than you. We have to let you go. What happened? Now suppose this is the number we observe. So what really happened? If we can, well, let's denote S the event that a task is a success. Ti is the event that the task is task I, with I equal to 1 and 2, right? There are 2 tasks. And we use B to denote the event that Bert is performing the task. And the complement of B is that Jim performs the task. If we could use the successful rate to approximate the conditional probability, indeed, conditional on the joint probability, the conditional probability of S, success, conditional you are doing task, Bert is doing task 1, is indeed higher than the conditional probability of S, conditional on Jim is doing task 1. And the same goes for task 2. So the probability that you succeed at task 1 and task 2 is higher than for Jim. However, if we aggregating across the 2 tasks altogether, well, the conditional probability of success given Bert is doing the job is unfortunately lower than the probability of S given Jim is doing the job. Well, what goes wrong here? You can pause your video here and think if you can figure yourself. Now, if we look at what's really going on, let's link the conditional probability of S given B to what we have already calculated, right? And also the P S given B, James, the conditional probability of S given James is doing the job with the value we have seen before. Okay, according to law of total probability, we know these 2 conditional probability can be calculated in this way. So the conditional probability of S given B equal to the conditional probability of S given T1 and B at the same time times the conditional probability of T1 given B. Right? This is the conditional probability version of the law of total probability. So suppose we are taking this as the new function, new probability function, right? The conditional probability is also a conditional probability is also a probability function. So now we apply law of total probability to this probability function, and you see it holds for this formula. Okay, that is because T1 and T2 is a partition of the whole sample space. So now, what really goes wrong here is if we take a look of the total tasks we have done for those 2 peoples, Bert and Jim, Bert is more likely to take in task 1, and Jim is assigned with more task 2, right? So if we simply aggregating them all together, essentially this one is taking the major weights in the first equation, right? The probability of S given B has their major contributions of the first term. While as for the second equation, because this value, James is more likely to do task B, so the PS, the value of the PS given BC, mostly come from the second term. If we are compare these 2 values naively, we are actually more like comparing the successful rate for Bert doing task 1 with the successful rate of Jim doing task 2. So we are comparing 2 different things. That's why we could not averaging simply events that are not comparable. You could draw a very weird conclusion here. So this is what we learned from the above 3 exercises. we need to be careful with conditioning probabilities, right? We need to be careful when we apply conditioning. So in the first exercise, we say omitted conditioning variable, omitted conditioning event could change our understanding of some phenomena. In microeconometrics, well, this is sometimes referred to as the endogeneity issue or omitted variable issue. And we need to be careful. We want to draw some causality conclusion working with conditionings, right? To work out causality, sometimes we need more than simply conditional probabilities. And it's a very hard job. It's very challenging to do a very decent research or data analysis. The second exercise basically shows that if we're mistaking the probability of A conditional on B with PB given A, we could draw very wrong conclusion as well. And the third one basically shows that don't average events that are not comparable. So if we want to do compare, be careful when we apply the conditional probabilities. So conditioning in general is not easy. And it's not easy for many experts in fields. To understand the conditioning well, we need to practice a lot. And good luck with understanding the conditioning. Hope you can learn something with those 4 exercises, and thank you for watching this video.